Good evening, all. Welcome to the live interaction section for our course Computational Fluid Dynamics. This is the live interaction session for week 9. So, till last week, we have seen solution for Navier-Stokes equation for incompressible flows. In week 9, we have seen some basic methods like Gauss-Seidel method, tridiagonal matrix, tridiagonal matrix algorithm like TDMA method, and all those methods by which we can solve the linear equations. So by now we would have understand that our Navier-Stokes equation will be for any problem, for any CFD problem. The Navier-Stokes equation will be modified according to the physics of the problem, and it will be suitably converted into linear, algebraic equation using discretization methods, suitable discretization methods, and then these linear algebraic equation has to be solved to get our answers or our flow field. So in week 9, this solution of linear algebraic equation and methods for solving the linear algebraic equation have been discussed, and in week 9, most of the methods that were discussed were in basic level. So let's start our session for our week 9 contents. So let's move on to the questions. So question 1. So I will give you the question and take some time to think on it. You would have watched the videos. Please try to recollect what you have learned or understood from the videos and try to answer the question. Then I will explain the answers. First question: which statement among the following is false about Gauss elimination method? Options are: option A, it can be computationally expensive for large systems. Option B, it is a direct method for solving linear systems. Option C, it is not suitable for sparse matrices. Option D, it involves raw operations for elimination. So our question is on a false statement. Which among the following is a false statement regarding the Gauss elimination method? You have 4 options. Try to answer the question. You can inbox your answers. And the answer is option C. That is the false statement among the 4 statements that we given for answer question. First question is our option number C, that it is not suitable for sparse matrices. By definition, sparse matrices is a matrix in which there are a lot of zeros, actually, zero elements. So, of course, definition for sparse matrix. Uh, but it's a false statement because Gauss elimination can be used for sparse matrices also. Uh, while filling in, Gauss elimination can fill in many zero entries and make the sparse matrices more dense. But this process can add up to our computational cost and increasing memory. For there are because of which there exist some specialized variation of Gaussian elimination that can handle our sparse matrices more efficiently. So the statement that it is not suitable for sparse matrices is wrong. So the question was to find out a false statement among the four statements. So option C is the right answer. Hope you got it. Moving on to next question. Next question is on TDMA method. Which of the following statement is not true? That is false about TDMA method. TDMA stands for, as you might have seen the videos, tri-diagonal matrix algorithm. So, which of the following is not true about tri-diagonal matrix algorithm? Otherwise, TDMA method. Options are option A, it is highly efficient for solving tri-diagonal systems. Option B, it is an iterative method that requires an initial guess and repeated calculations. Option C, it is particularly useful in CFD for solving discretized governing equations. Option D, it can be applied line by line in multi-dimensional problems. So again, in second question also, here are four statements and the question is asking to find the false statement about TDMA method. You can try to answer. Options are, it is highly efficient for solving tri-diagonal systems. Option B, it is an iterative method that requires an initial guess and repeated calculations. Option C, it is particularly useful in CFD for solving discretized governing equations. Option D, it can be applied line by line in multidimensional problems. So recollect what you have studied in the from the videos and try to answer the question. You can inbox your answers. From the options itself, we can simply find out the answer. We can eliminate some true statements from here. So TDMA, first statement is saying that it is highly efficient for solving tri-diagonal systems. From the name itself, we can see that one is true. And uh, option B is an iterative method. Let's keep that option aside. Moving on to next one, it is particularly useful in CFD for solving discretized governing equation. This is also true statement. Next one, it can be applied line by line in multi-dimensional problems. So these two are kind of the tough options here. So if you look here, this word iterative method. So TDMA is not an iterative method; it's a direct method. So this is a wrong statement. And option D is a true statement because it is up the approach is line by line approach in multidimensional problems. So our answer is option B is the wrong statement or the false statement regarding TDMA, that it is a iterative method, because TDMA is a direct method, and uh, direct method, mostly in direct methods, give solution in a finite number of steps, while for iterative method you'll have to keep on iterating till our solution falls within the limits of a fixed tolerance. In iterative methods, mostly starts with an initial guess, and the iteration, that is the calculation, repeated calculation, will go on till some there will be some particular error limit we will set, or called tolerance. If I am willing to take errors up to 10 minus 6, at the point of 10 minus 6, I am willing to take that much errors. That is from very small value up to 10 minus 6. Beyond that's I am not talking with 10 minus 5 or minus 3. Then this will be my tolerance set limit, or similar to that. So whenever this repeated calculations error will fall below this 10 raised to minus 6 range, at that time, until that time, we will have to repeat the calculations. So such methods are called iterative methods, TDMA, whereas TDM is a direct method. Moving on to next question. Next question is again on TDMA method. Options question is, what type of metric structure does the TDMA method works best with? Question is asking about the metric structure with which the TDMA can work best with. Options are: option A, full matrix; option B, sparse matrix; option C, banded matrix; option D, diagonal matrix. So these are four different kinds of matrices. We have already discussed about sparse matrix in first question. So keeping that in mind, try to answer the question: which kind of matrix is best suited for the TDMA to work with? So let me explain what is these matrices are. A full matrix is also known as full rank matrix. It is kind of the number of linearly independent rows of columns, actually. Linearly independent number of columns in a matrix. Or it can also uh, explained as which is the smallest dimension of the matrix. Because if you are reducing it in a smaller matrix, then what will be the, if the rows are independent to each other, suppose one row is multiple of other or something, then we can reduce the matrix. So the extent or the smallest dimension of the matrix after reduction is called full matrix. Sparse matrix, we have already seen that with the matrix having a lot of zero elements, and banded matrix is like a matrix is having uh, elements as in the form of bands. it will represent some bands. Diagonal matrix is matrix where having elements in diagonal shape. Suppose this is a matrix. Then if there is only elements in the diagonal, then it's called diagonal matrix. Diagonal matrix also a banded matrix. So our question is, what type of matrix structure does the TDMA method best works with? Our answer is C, banded matrix. And diagonal matrix also is a type of banded matrix. Our answer is option C, where tridiagonal matrix simply explains us this is the, if this is the major diagonal, then one row of elements, I mean one diagonal element above and below, this constitute tridiagonal. So this is main diagonal and one set of diagonal elements above, one set of diagonal elements below. Such a matrix is called tridiagonal banded matrix. So such kind of matrices is with which the TDMA works best with, and other elements will be mostly zeros. So in that sense, we can also say sparse matrices also are better, but it should be convertible to a banded matrix. Then only TDMA method can be used. Moving on to next question. Okay. In a finite volume discretization, the advection equation in CFD, which of the following variables would typically result in a tridiagonal coefficient matrix? So the question is, if we are following FVM, that is finite volume method, for the advection equation, then which of the following variables would typically result in a tridiagonal coefficient matrix? Options are option A, density, option B, velocity, option C, pressure, option D, all of the above. Try to recollect the advection equation we have discussed in the earlier classes and try to answer the question. So advection equation will be dou phi by dou t plus u times dou phi by dou x is equal to 0. This will be the advection equation. So from this itself we can understand that option B, velocity, would be the variable that would typically result in the tridiagonal coefficient, I mean tridiagonal TDMA formation. When displaced using finite volume methods. Moving on to next question. The next question is also on TDMA method. The question is, when applying TDMA in a CFD code, how are the boundary conditions incorporated? So the question is on boundary condition, how the TDMA method handles the boundary conditions. Options are: option A, they are directly included in the tridiagonal matrix coefficient. Option B, they are treated as separate condition after solving the system. Option C, they are not relevant for TDMA algorithm. Option D, they require modifying TDMA algorithm itself. So the question is on how to incorporate boundary conditions in TDMA method for a CFD code. Try to answer the question. For solving the linear system of equation in CFD involves forward and back. The question is on how to incorporate boundary conditions for TDMA method. So, if you recollect the first few lectures, and then the it will be easy to eliminate the uh, options. So from the initial uh, first and second week's videos itself, you could have understood how boundary conditions, that is BCs, are incorporated. So the suppose for a linear uh, one-dimensional problem, so this point, suppose this is 0 and nth node, then these nodes here, the boundary conditions will be applied and it will be discretized along with the code. So that is the basic method to incorporate boundary conditions in CFD code. So uh, by keeping that in mind, if you check that, you can see that options, we can simply eliminate some of the options which are wrong. So from option while checking option A, that is they are directly included in the tridiagonal matrix coefficient. So if you have watched Week-9's videos, then you would understand how TDMA metrics are incorporated. Like we will be writing the algebraic equations. And these coefficients of algebraic equations will be written uh, to make this tridiagonal matrix. So while writing the algebraic equations itself, these boundary conditions are incorporated in the algebraic equations. So, okay, and after uh, creating the algebraic equations, we are formulating the tridiagonal matrix. So, if you recollect that, from that itself, option A is the right answer. And uh, if you can, while checking others also, it is seen. It can be seen that the other statements are entirely wrong. Like second statement is saying they are treated as separate condition now. There are some methods where we need to have special treatment for uh, incorporating boundary condition, but TDMA does not request that. So option B is wrong. Uh, Third statement is like they are not relevant for TDMA algorithm. Obviously, boundary conditions are always relevant, so that is also wrong. Option D is like they require modifying the TDMA algorithm itself. TDMA is it's in itself is an algorithm. So how uh, the entirely changing TDMA algorithm is not needed. Only we need to if and when it requests, we only need to modify the boundary conditions to incorporate it in the coefficients of algebraic equations. So option D also wrong. So our answer is option A. That is, the boundary conditions are incorporated by modifying the corresponding coefficients in the tridiagonal matrix based on specific boundary types. We have studied different boundary condition types like Dirichlet method, Dirichlet condition, Newman condition, and Robin condition. So depends on that type of boundary condition, it will be treated accordingly and incorporated as the coefficients of the algebraic equation, which is then converted into tridiagonal matrix. Hope everybody got that. So moving on to next question. Next question. Compared to other methods like Gauss elimination, what is the potential advantage of TDMA in CFD applications? So the question is asking what is the advantage of TDMA in CFD application in comparison with methods like Gauss elimination method. Options are option A, it handles full matrices more efficiently. Option B, it is more memory intensive. Option C, it is specifically designed for tridiagonal systems leading to computational efficiency. Option D, it requires less user intervention. So the question is asking for the potential advantage of TDMA for using in CFD calculations over methods like Gauss elimination method. Try to answer the question. So if we can check the options one by one, then it will be easy for solving them. Solving them. So let us check the first uh, option. It says that it handles full matrices more efficiently. So we have already discussed what is full matrices. Full matrices is also called full rank matrices. So full rank matrix is something that have uh, having a lot of non-zero elements and which cannot be reduced further. I mean, it's like there is no two dependent rows are there. So such a matrix is called full matrices. But uh, Gauss elimination type method is best for solving full rank matrices or full matrices. So this option A is wrong. So it's because Gauss elimination method has an upper hand for solving full matrices or matrices that cannot be reduced further. Then Gauss elimination methods comes into picture where by using raw operations the matrix is reduced to a upper triangular matrix. So option A is wrong. And next option is it is more memory intensive. So what does the term memory intensive mean? Memory intensive means that we will need a lot more memory or storage space, or uh, like if you know RAM and all, uh, temporary storage is called memory. So while calculating, if the calculation needs to temporarily store a lot of data, then it will need more memory to do that. So uh, it requirement of larger memory is not at all a advantage. So the statement B itself is a negative statement or disadvantage statement. It's not a merit for a method to become memory intensive. So our question here is like potential advantage. So option B is also wrong. Then option C, it is specifically designed for tri-diagonal systems leading to computational efficiency. Option C is the right answer. From this itself, we can see that say that TDMA method is tri-diagonal matrix algorithm method, which is specifically designed for tri-diagonal system, which for improving the computational efficiency. Option D, it requires less user intervention. Uh, that is wrong because TDMA requires a good amount of user intervention. So option D is wrong. So our answer is option C, that it is specifically designed for tri-diagonal systems uh, to increase the computational efficiency. So uh, earlier while developing the CFD codes and all, the people working for the same has noted that mostly uh, when partial differential equations PDEs is converted to algebraic equations and reduced, it mostly has resulting into sparse matrices or the matrix having more zeros. So again, while discretizing some classic problems like addition method and all, addition equation and all, people have seen that it is reduced into tri-diagonal or pentadiagonal systems. So from this realization that these sparse matrices are mostly resulting into banded matrices like tri-diagonal or pentadiagonal matrices, this TDMA method has been developed to easily and efficiently uh, solve the system to get the results. So TDMA method does not require data storage or memories and also do not need a lot of unnecessary computation like raw reductions to get the answer. That's why uh, it has an upper hand over Gauss elimination kind of methods. Moving on to next question. Which of the following properties of a CFD problem might make TDMA less suitable as a solution method? So the question is asking to pick a scenario that would where TDMA will be less suitable. Options are: option A, linearity of the governing equations; option B, steady nature of the flow; option C, complex geometry with irregular boundaries; option D, high Reynolds number flows. So question is asking which among the following scenario or CFD problem will make TDMA less suitable or less efficient. Try to answer the question. So we have seen that if we can check the options, then it will be easy. Linearity of the equations is a good thing for TDMA or for that matter any direct method. So linearity of the governing equation is does not make the TDMA method uh, less suitable. It's a good thing. And also moving on to next question, steady nature of the flow. That is, uh, there is no time varying times. So that also is well suited for TDMA method. Moving on to next question, complex geometry with irregular boundaries. So this is our answer, option C, complex geometry with irregular boundaries. So this complex geometry with irregular boundaries, while discretizing, may not easily reduce to tridiagonal systems. So there, T-diagonal method won't be working well. Also, high Reynolds number flows can also be solved with TDMA method. So D is also option D is also a matching scenario for TDMA method. Our answer is option C, that is complex geometry with irregular boundaries. Because I have already told you that we have already discussed that in general pipeline of CFD, like PD will be uh, converted to algebraic equations, and boundary conditions will be incorporated in algebraic conditions. And when this the geometry is complex with irregular boundaries, incorporating these boundary conditions and converting them into algebraic equation and then creating a coefficient matrix. So when the geometry is complex, this process, that is converting the boundary conditions or boundary elements to algebraic equations, may not easily result to a tridiagonal, simple tridiagonal structure for the coefficient matrix. So we will have to reduce it into a tridiagonal matrix to use TDMA method. Whereas for advection equation and all, mostly for advection equation and other kind of geometry, while uh, while converting itself to while converting the partial differential equation into algebraic equation itself, the algebraic equation will reduce to a tridiagonal coefficient matrix. So it will be a direct I mean, it will be easy to get a tridiagonal matrix, coefficient matrix out of the algebraic equations. Whereas when the geometry is complex with irregular boundaries, this process will be difficult, which makes the TDMA less effective in those cases. Moving on to next question. How can the TDMA method be used in conjunction with other numerical techniques in a CFD simulation? So the question is asking, when using with other methods, what will be the role of TDMA method in a CFD solution? We have discussed different numerical techniques in previous week's videos, previous videos and our interaction sessions also. So if you can recall that, so what will be the role of TDMA method in comparison to the other numerical methods in a CFD simulation? Options are: option A, it can be used as a pre-processing step to prepare the system for a more complex solver. Option B, it can be employed for specific parts of the domain with a tridiagonal structure. Option C, it cannot be combined with other methods effectively. Option D, it is the primary solver for most CFD problems. So, what is the uh, role of TDMA method if it is used with other numerical techniques in CFD simulation? Is it a pre-processing step? Is it a specific solver for a specific domain, or whether it cannot be used with along with other methods, or is it a primary solver in CFD problems? Try to answer the question. answer is option B, that it can be employed for specific parts of the domain with tridiagonal structures. So that is, we have seen other methods where artificial compressibility method and all such methods are pre-processing steps, whereas TDMA method is a direct standalone method, but it can be a valuable tool for hybrid approach. Suppose we have a large domain, and suppose one particular domain of uh, our geometry will our computational domain will end up into a tridiagonal structure. With the coefficient matrix will end up into a tridiagonal structure. Then we can use TDMA method for that particular computational domain, where it offers where it can work more efficiently. Mostly, uh, we won't be using such things, but still, mm, the for our question, that is why if it is if it has to be used along with other methods, then it is better to employ it for specific parts of the domain where computational domain is having the uh, tridiagonal structure. Also, we have seen that TDM method is not good for complex uh, geometries with irregular boundaries. So, such uh, such regions or such domains can be used or solved with uh, other methods, while the part of the domain which is having the tridiagonal coefficient structure can be solved easily with TDMA method. Moving on to next question. Next question is, what is the computational complexity or order of operations of the TDMA method for solving a tridiagonal system of size n? So the question is asking the order of operations or the amount of operations needed for TDMA method for a tridiagonal system of size n. Options are: option A, order of n cube; option B, order of n square; option C, order of n log n; option D, order of n. So suppose our tridiagonal system is having a size of n. So what is the order of operation that is needed for solving that system using TDMA method? Try to answer the question. So for anyone that doesn't understand what is computational complexity or order of operations, that in the field of computational computational mechanics or computer science, this computational complexity is often uh, understood as the requirement or the need for uh, time or space uh, for the algorithm to solve a particular function or equation. So here, the for safety, it is like suppose this is having n elements. What time? How much? Here the question is about what's the time complexity, number of operations, or the time or number of operations it has to carry out. So this suppose it has an this n is an input size. Suppose the system is having an input size of n, then what is the number of operations? So this is something called the big O notation. Big O notation or order uh, to uh, express how uh, this big O notation shows that how the output varies as the input grows. So here the input size is like the size of the system. And then what is the here it is asking for the order of operation. So with big O notation, it is trying to estimate uh, how much will be the uh, order. Suppose it's uh, we write 10 raised to 2 or 10 raised to 4. That is in the fourth order. That means it is mostly in the fourth order. So here uh, not 10, we are using n. Suppose the system is having n variables, then what will be the number of operations needed to solve that system? So it will be in order in the order of like it, 10 square means in hundreds, like anywhere from 100 to 999, that kind of thing. So uh, that is what the question is asking. So here the question is asking what will be the number of operation needed for or order of the number of operations needed for a tri-diagonal system of size n. Our answer is option D. That is, it will only need order of n. That is, suppose the system is having n size is n, then we will only need uh, operation of n times or in the order of n. Suppose we have what only have once or the size of in is in below 9 or something, then the operation will also be in that time, like in below 100. So uh, this not below 100, it will be in, it won't go up to n square. That is the notion here. So TDMA is a method where we will be uh, forward elimination and back substitution. That kind of method will be there. It has a two-step or two-go approach, forward and backward approach. Going forward, it will reduce the equations, and coming backward, it will substitute and solve the equation. That kind of method TDMA is using. You might have watched these videos. So for TDMA, the computational complexity is always in the order of n, whereas in Gauss elimination, it is up to n cube. The order of operations needed for Gauss elimination method is in the level of n cube. Moving on to next question. Next question is on vorticity stream function method. How does the stream function vorticity method handle viscous effects in the incompressible flows? Options are: option A, it directly incorporates viscosity term in the governing equations. Option B, viscous effects are neglected, making it suitable only for inviscid flows. Option C, viscous terms are included through additional source terms in the vorticity equation. Option D, the method is not applicable for viscous flows due to the limitations in vorticity formulation. So the question is about stream function vorticity method, and how does this, this stream function vorticity method handles the viscous effects in incompressible flows. We have also discussed about this in the last interaction session. So please try to recollect those and try to answer. Your answer is, we have also discussed in the last discussion section. So the answer is option C, that is the viscous terms are included through additional source terms in vorticity equation. People can get confused between option A and option C, but uh, incorporating this first statement is only saying that it is incorporated in governing equations, but actually it is added as additional source terms. It's not there in governing equation. We will have to add it as additional source term in the vorticity equation, because this is a two equation formulation where we will be having an equation for stream function and another equation for vorticity. So this stream function vorticity method or vorticity function method, this viscous terms has to be included in the vorticity equation as additional source terms. Our answer is option C. Moving on to next question. The question is on limitation of stream function vorticity method for boundary condition involves which of the following? So question is asking what is the limitation for the stream function vorticity method for the boundary condition listed below. Options are: option A, specifying both stream function and vorticity at all boundaries. Option B, difficulty in implementing no-slip conditions on solid walls. Option C, inability to handle flows with free surfaces. Option D, all of the above. So the question is asking which of the following or which among the following boundary conditions has a limitation with stream function vorticity method. So if you remember stream function and vorticity method, in stream function and vorticity method, we will have to convert all the UVW, that is the velocity components, into stream function and vorticity. So basically, we will have to convert all the boundary conditions also into stream function and vorticity. So uh, incorporating boundary condition in stream function vorticity method itself is a challenge. So the options that specifying uh, both stream function and vorticity at our boundary itself is a challenge or limitation. Also, implementing no slip condition, because there is no alternative for no slip in as in case of velocity for stream function or vorticity. And also when there is free surface in a flow, there also this stream function and vorticity method struggles. So our answer is option D, all of the above. All these scenarios has limitations or creates challenges for stream function vorticity method. Our answer is option D. Next question. Which method for solving the linear system of equation in CFD involves forward and backward substitution steps? So as we have discussed before, uh, different types of methods for solving linear equation uh, operates differently. So which among the following has an as a forward and as well as backward step? So options are option A, Gauss elimination; option B, Jacobi method; option C, LU decomposition method; option D, relaxation method. So we have already discussed about TDMI method and Gauss elimination method. So you have an pretty much outline about the two methods. So here the question is about which method among the following uses forward as well as backward substitution steps. Try to recollect from the videos and try to answer the question. So answer is LU decomposition method. In LU decomposition method, as other words, L and U denotes the, we have a coefficient matrix. Suppose we have a coefficient matrix A, then it is decomposed into uh, two matrices, that L and U. So this L is a lower triangle matrix. Yes, it is a lower triangle matrix, and U is an upper triangle matrix. And uh, both these matrices are solved separately to get the unknowns. So, essentially, what we have is like our algebraic equations. Algebraic equations will be converted into a form like Ax is equal to B, where A is the coefficient matrix, X is the unknowns, B is the uh, right hand side or the conditions matching. So we will have to solve this I mean reduce this A to solve the system of equations. So here the matrix A itself is decomposed into two matrices L and excuse me. So here the matrix A is decomposed into a lower triangular and upper triangular matrix, and then uh, it is solved by forward and backwards substitution. In forward substitution, this L matrix is equated as Ly is equal to B to solve for y. Then this y is equated to ux, where x is the unknowns and u is the upper triangle matrix. So in backward substitution, the method is ux is equal to y. Then it is, so this y is solved from here, and then uh, with this y values, b is known, and with this known b, we are hence this lower triangle matrix L is a lower triangle matrix. We can solve for y, then we will get the y values. Then with these y values, we will be solving this ux is equal to y to get x values. So that is how this LU decomposition method works. Okay, moving on to next question. In a Jacobi method, the update equation for a variable involves its current value and the values of its neighbors from the dash iteration. So the question is about Jacobi's method. So in Jacobi's method, we know that the update equation has current values as well as the uh, what values of neighbor. So which values of the neighbors is taken for update equation in Jacobi method? That's the question. So options are: option A, previous iteration; option B, current iteration; option C, next iteration; option D, average of all. So the question is essentially asking about the update equation for Jacobi equation. So how does the update equation of Jacobi method is formulated? Half the half part is given the question, that is it uses current value of the variable and which value of the neighbors is taken for the iteration. That's the question. Try to recollect and answer the question. Our answer is option A, previous. So the Jacobi's method will use uh, the value of the current value of the variable and previous values of the neighbor cells. So Jacobi's method will be something like this. This A11 is our option, x1 is our variable, then this will be k plus 1 plus all other elements will be from kth step. That is a12 x2 from kth step plus etc. up to a1n xn of kth step, that is the previous step, is equal to b1. So this is one example for Jacobi equation, update equation. So only this, if we are solving for x1, so only this variable will be taken from the current step. All other equations, all other variables, neighboring terms will be taken from the kth step or the previous step. Moving on to next question. So the question is on artificial compressibility method. The question is asking the primary purpose of the artificial compressibility method in CFD is to. Options are: option A, directly solve compressible flow problems. Option B, simplify the pressure velocity coupling in incompressible flows. Option C, increase the density of the fluid being simulated. Option D, improve the accuracy of turbulence models. So we have discussed in detail about artificial compressibility method in previous session. Try to recollect and answer. So the question is asking the primary purpose or the utility of the artificial compressibility method in CFD. Our answer is option B, that is to simplify the uh, pressure velocity coupling in incompressible flows. So we have already discussed that uh, uh, artificial compressibility artificial compressibility method is a way of using compressible flow solvers for incompressible flows. So here what we will do is like we will introduce a fictitious compressibility term in the continuity equations, that is a fictitious density term which will iteratively reduced in a pseudo loop. So this uh, helps uh, this makes it suitable, makes the problem suitable to be solved using compressible flow solvers. So that is the use of artificial compressibility, that is to uh, solve the pressure velocity coupling issue in incompressible flows. Moving on to next question. The artificial compressibility method introduces a new variable. What is the variable typically called? So we have discussed in previous question that artificial compressibility method is used for pressure velocity coupling. So the method introduces a new variable, and what is the name of that, or what is the variable, the newly introduced variable typically called as? Option A, friction's density. Option B, pseudo velocity. Option C, artificial viscosity. Option D, pseudo Mach number. The answer is option A. That is, this newly introduced variable is called friction's density. Often this like normally our continuity equation will be del dot u is equal to 0, but in artificial compressibility method, then the continuity equation will be modified as dou by dou t of rho star plus del dot u is equal to 0, where this rho star is called friction's density. So this density is then related to pressure using a factor called compressibility factor called beta. So that's how we are introducing artificial compressibility in incompressible flow problems, or to make it suitable to solve with compressible flow solvers. Moving on to next question. How does artificial compressibility method achieve convergence to an incompressible solution? The question is asking, how does the artificial compressibility method achieve convergence to an incompressible solution? Options are: option A, by setting the pseudo density to a constant value. Option B, by iteratively reducing the magnitude of the pseudo repeatability time. Option C, by increasing the time step size in pseudo time iteration. Option D, by directly solving the continuity equation. Question is asking how uh, uh, artificial compressibility method can help in convergence of an incompressible solution. Try to answer the question. So our answer is option B, that is by iteratively reducing the magnitude of pseudo compressibility time. That is, we have already discussed that the new time will be added as dou by dou t of rho star in continuity equation. So this time, this pseudo compressibility time will be reduced using a pseudo time loop. So this has to be efficiently reduced to make it 0 or below some particular tolerance limit to get a proper convergence in our incompressible flow solutions. Moving on to next question. The artificial compressibility method can be considered a type of which methods? Options are option A, turbulence model, option B, preconditioning method, option C, discretization scheme, option D, boundary condition treatment. So the question is asking what is a type of artificial compressibility method? In which category does the artificial compressibility method lies? You can try to answer the question. answer is option B, preconditioning method. So our artificial compressibility method is kind of literally preconditioning or making an incompressible uh, sorry incompressible flow problem is preconditioned or conditioned to be run using compressible flow solvers. So it's basically a preconditioning method or preconditioning technique. Moving to next question. What is the crucial aspect or important factor to consider when implementing the artificial compressibility method? Options are: option A, selecting a high value for pseudo density; option B, choosing an appropriate time step for the physical time step; option C, determining the optimal value of pseudo compressibility time; option D, defining the complex turbulence model. So the question is asking that what is the crucial aspect to consider while implementing the artificial compressibility method. So we have already discussed that here this term is added additionally dou by dou t of rho star. So this pseudo compressibility term while using one second, give me 1 second. Okay, so this plus del u is equal to 0 is what we are uh, using it. So this, sorry, I am writing here. I would like there is more space here, so I will write here dou by dou t of rho star dou by rho t of rho star plus del dot u is equal to 0. So this rho star is taken as uh, is related with pressure with the relation P by beta square. So this is a pseudo compressibility term or factor. So while substituting in this equation, it becomes 1 by beta square dou P by dou T plus del dot U is equal to 0. So taking this term or pseudo compressibility term, this is a compressibility factor or compressibility term. This compressibility take this uh, choosing of this compressibility term should be taken with utmost care, or it requires because it is the one which mostly depends on how long the iterations will take or how easy it will converge. So this term should be taken with care, utmost care. So that's a and that's the answer to the question. That is choosing an optimal value for the pseudo compressibility term. If you are selecting a very high value, then it won't it will give the negative effects, whereas it doesn't have uh, it, it is uh, the choose selection of time step only matters similar to other time matching problems, but whereas this selection of this uh, value for this pseudo compressibility term has critical significance while using artificial compressibility method. Moving on to next question. The question is on stream function vorticity method. Which equation is solved for stream function in the stream function vorticity method? So the question is asking which equation is solved to get the stream function in stream function vorticity method. Options are option A, continuity equation, that is del dot u is equal to 0. Option B, Navier-Stokes equation, that is momentum conservation equations. Option C, Poisson equation for pressure, that is del square P is equal to dou omega by dou T. Option D, the biharmonic equation derived from vorticity stream function relationship. So which of the following equation is solved to get the stream function in the stream function vorticity method? Our answer is option D. That is, a biharmonic equation is used to derive vorticity stream function relationship. So we know the velocity components u and v. For the biharmonic equations are u is equal to dou psi by dou y, whereas v is equal to minus of dou psi by dou x. These are the biharmonic uh, equations used to find the stream function, where psi is the stream function. So these two equation 1, 2, these two equations are used to find the stream function, and then vorticity is given by mega vorticity is given by dou v by dou x minus dou u by dou y. So it will become omega can be written, or omega or vorticity can be written as a function of stream function. That is, it will be like if you use these equation 1 and 2 to write omega, it will be like dou square psi by dou x square plus dou square psi by dou y square is equal to minus omega. That will be the relationship between stream function and vorticity. So that is, our answer is using a biharmonic equation. That is, this is the biharmonic equation, u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. These are the two equations to form stream function. Moving on to next question. Which numerical discretization techniques are commonly used with stream function vorticity method? Options are: option A, finite difference method on structured grids; option B, finite element methods on unstructured grids; option C, both finite difference and finite element methods; option D, spectral methods for higher accuracy solutions. So the question is asking which are the types of numerical discretization techniques that are compatible with stream function vorticity method. In the previous interaction session, we have discussed that stream function vorticity method is have its own limitations, that it will work only on 2D and such scenarios. So here the question is asking which are the types of numerical discretization techniques that can be used with stream function vorticity method. Take your time and try to answer the question. Answer is option C. Mostly it only works with finite difference method on structured grids, but theoretically it is also fine to work with finite element methods. So since there is an option incorporating both finite difference and finite element methods, we can only choose that. Our answer is option C. Both finite difference and finite element methods are suitable for discretizing the governing equations in stream function vorticity method. But this is having less applicability and less used. Only it is theoretically possible. Theoretically, feasibility is there. So that's why we are choosing option C, both finite difference and finite element methods. Next question. The stream function vorticity method is particularly well suited with for which type of flows? The stream function vorticity method is particularly well suited with which type of flows? Options are option A, high speed compressible flows with shock waves. Option B, turbulent flows with complex vortex structures. Option C, steady or time independent incompressible two-dimensional flows. Option D, flows with strong pressure gradients and separation. So the question is asking which of the following flows is best suited for solving with stream function vorticity method. This aspect we have discussed in last session also. Try to recollect and answer the question. The answer is option C. The answer is option C. That is steady time or time independent incompressible two-dimensional flows. So we have already discussed that the stream function is a 2D concept, so it can only work for 2D flow problems. And also, this stream function vorticity method is uh, designed for incompressible flows. So with that in mind, we can see that only the two types like incompressible and 2D flows is only appearing on option C. So our answer is option C, that is stream function vorticity method is particularly uh, suitable for steady time independent incompressible two-dimensional flows. Also, this it relies on the continuity equation being satisfied by the stream function. That which is what the we explained in the biharmonic equation in the last question. Moving on to next question. This is a simple one compared to others. The question is asking the stream function vorticity formulation solves for which of the two fundamental variables in two-dimensional incompressible flows. Options are option A velocity component u and v, option B pressure and vorticity, option C stream function and vorticity, option D velocity, magnitude and direction. So from the name itself we know it is stream function vorticity. Stream function and vorticity are the two variables that is being solved in two-dimensional incompressible flows. Moving on to the next question. Which property of the stream function is crucial in the stream function vorticity method? Options are option A, it represents total mechanical energy of the flow. Option B, its gradient is perpendicular to the velocity vector. Option C, it directly relates to the pressure field. Option D, it defines the circulation around the closed curve. So, which aspect or which property of the stream function is crucial in stream function vorticity method? Our answer is option B. That is, its gradient is perpendicular to the velocity vector. That we have already discussed about the relation between u, v, and uh, stream function psi. So u is equal to dou psi by dou y, and v is equal to minus dou psi by dou x. That is, if you see here, these are the gradients. Gradients of psi is perpendicular to the velocity vector. So u and v are the components of velocity, and its gradient in y direction gives u, and negative gradient in x direction gives v. So this property of the stream function makes it well suited to use in uh, to substitute for u and v in CFD calculations or stream function vorticity method. Next question. What is the significant advantage of stream function vorticity method? Options are option A, it directly solves for the pressure field, eliminating need for pressure velocity coupling. Option B, it computationally more efficient than solving for velocity components directly. Option C, it can easily handle complex boundary conditions. Option D, it is particularly suited for turbulent flow problems. So the question is asking the advantage or significant advantage of stream function vorticity method. Even though we have seen that uh, stream function vorticity method have uh, serious challenges or serious limitations, then what is the significant advantage we are getting for utilizing stream function vorticity method. You can try to eliminate between the options to get the answer. Our answer is option A. That is, it directly solves for the pressure field and eliminating the need of pressure velocity coupling. So this stream function vorticity method we have learned as a subpart for solution for incompressible flows, where this is a method for uh, solving the issues related with pressure velocity coupling. So here in stream function vorticity method, by solving stream function and vorticity, the method automatically satisfied for the incompressibility constraint. That is, divergence of velocity is equal to 0. This constraint that is already being satisfied by the stream function vorticity method. So we don't have an additional uh, burden of solving pressure velocity coupling. So that is a significant advantage of this method, but it has serious limitations also. So that's all. That's all for today's session. Thank you everyone for joining.